So flipping through this is good because it reminds you again the things that we learned before. So let's combine this knowledge now we have about the reactions of CO2 dissolving in the ocean, the buffering system in the ocean, and look at the profiles of pH, right? So this should now be somewhat easier because now you can combine your knowledge of the CO2 profile, the buffering reactions, buffering ability, and the movement of the carbonate bicarbonate ions and calcium carbonate rain, calcite rain, and how much makes it to the bottom, etc., with the pH profiles. And as you can imagine, based on your knowledge, you expect the pH profiles to be the mirror images of CO2 profiles, right? So CO2 was low near the surface, so you expect pH to be high near the surface. It's more alkaline. As you go deeper, CO2 is increasing and reached a maximum around 1 kilometer in the North Pacific, whereas it was increasing but not so much in the North Atlantic. As we said, it has to do with the water sinking from near the surface. So you can imagine here, if the North Atlantic, for example, has surface water sinking, that means the low CO2 waters are sinking and they are actually decreasing the CO2 below the surface. Whereas if there is no water sinking, that means the respiration is beginning to accumulate CO2 in the deeper ocean of the North Pacific. Right? Intuitively, it begins to build a story in your head. So the pH, on the other hand, drops because CO2 is increasing so much in the North Pacific. So it's a mirror image of the CO2 profile, which itself was the mirror image of the O2 profile. So O2 profile looks like pH, but that's not directly related. It's pH is related directly to CO2, but CO2 is related to O2, and so on. So again, pH increases as you go deeper in the Pacific Ocean. Turns out that it's because the waters are older and they're accumulating more CO2, whereas in the North Atlantic it's not increasing that much. It's much less variable from the surface to the bottom, because if the waters are sinking and biology is happening, respiration is happening, that is decreasing the CO2 as you expect below the surface. But because of this mixing of the near surface waters, that decrease is not as high as in the Pacific Ocean. So, and with depth again, it doesn't increase as much as in the North Pacific. These are the things to remember. Alkalinity in the ocean is a very complicated formulation. It's the net H plus ions. We will probably see a formula later on, but that again is related closely to salinity variations, right? When we say salinity increases and water sink in some parts of the ocean, then obviously salt is a big part of the density equation as well. Temperature is important, but salinity is also important. So how does salinity vary? We'll see some figures again later on, but at high latitudes, you had already seen the evaporative latitudes moving water into precipitative latitudes in the polar regions and dumping a lot of rain, which means you have low salinity at high latitudes. You also have a lot of sea ice melting, in addition to also river runoffs. For example, the Arctic Ocean, which is almost completely surrounded by land all around it. Canada, Siberia, the Russian parts, Norwegian parts, and Greenland and so on together form lots of rivers and sea ice melting and so on. Arctic tends to be very fresh, which actually is good for freezing ice as well. As we know, salt reduces the freezing temperature, so less salt means it can freeze at a higher temperature, and so on. So all these add to having a low salinity at high latitudes. As you come to low latitudes near the equator, again, remember we said the evaporative latitudes are in the subtropics and not in the tropics, and I had said because lots of evaporation happens in the tropics, but also a lot of rain happens in the tropics. So this high rain actually ends up giving us relatively lower salinity near the equator, because you precipitation. High precipitation also means a lot of rivers, right? You have the Amazon, the Ganga, all the rivers in India, Krishna, Mahanadi, and so on, and lots of rivers in Indonesian regions, etc. So lots of runoff as well as a lot of rain. So low latitudes, we will see, have relatively lower salinity. Mid latitudes, which were shown as the high evaporative bands, have high salinity. They are warm, they are dry. Warm also favors evaporation, which increases salinity in the ocean water. They are dry because the precipitation is not very high, which is why evaporation is higher than precipitation. And we will see when we do the atmospheric circulation that the air is actually sinking in these regions. Sinking air makes for clear skies, high pressure, low rain. Rising air takes water with it, expands, creates clouds and rains. And it's associated with low pressure because rising air means warm temperature means low pressure. So subtropical latitudes, or we call it mid-latitudes here, but typically they are subtropical is the better word. They are warm, they are dry, and there is descending air, which is increasing evaporation. So this is the basic story, but we'll come back and refine it some more with good figures.